This is all about the basic examples. Also, I would say the basic knowledge of the this electrophilic substitution reactions. Now we will see few of the examples also about the Friedel-Crafts reaction. The first illustration which I would be I would like to share with you is that suppose I have a benzene and you take dichloromethane, that is CH2Cl2, and you react it with the AlCl3. So what will gonna happen is that first of all CH2Cl2 will react with the AlCl3, and hence it will be forming CH2 positive Cl. Now this is electrophile, so what will happen is that the benzene ring, that is a reactant which we have taken in this reaction, will attack on this CH2 positive Cl, and therefore it will form benzyl chloride. Now basically this benzyl chloride is not a aryl halide. First of all, I repeat that this benzyl chloride is not an aryl halide. Why? Because aryl halides are those where you have a halogen directly attached to the ring. But in this case, that is benzoyl chloride, halogen, that is Cl, is not attached to the ring directly. So it is considered as Rx only. Now what will happen in this reaction is basically, once you get the benzyl chloride, it is the Rx, and you have a benzene already in the solution. So what will gonna happen is that this benzyl chloride will react again with the AlCl3 and forms a benzylic carbocation, which you know very well that it is a stable carbocation. So therefore, now this benzyl carbocation now will functions as a electrophile, and benzene ring will attack that again on this benzylic carbocation, and hence the product formed will be basically biphenyl methane. So basically in this question what you have learnt is that the reaction does not stop at the first step itself. It might go forward also if at all the reaction conditions are there for any of the example of the electrophilic substitution reaction. Likewise in this case we did the Friedel-Crafts reaction twice because there was a possibility of it. So similarly in other examples also you have to think whether any side reaction or any further reaction is possible or not. If at all it is possible, so you carry out the reaction, after that the product formed will be your major product, or you would say that the final product. So therefore in this example, the new thing is that if you have something like CH2Cl2, or I give you another example also, chloroform, that is CHCl3. In this case, Friedel-Crafts reaction takes place thrice, and hence the product formed is basically triphenyl methane. So you can try it out also yourself, that how does a reaction of the benzene with the chloroform in the presence of AlCl3 takes place to form triphenyl methane. Now this is all about the electrophilic substitution reaction. Finally we will be discussing is the the chemical reactions of the aryl halides. And in the chemical reactions of the aryl halide, the most important and the most commonly known reaction is the Dawes process, that is Dawes process, in which what we do is we react chlorobenzene with the aqueous NaOH and it forms phenol. But this reaction does not take place under the ordinary conditions. It takes place basically under high temperature and pressure conditions, and this is why, because the reaction over here is taking place is basically the nucleophilic substitution. And I had told you when I started with the aryl halides that the aryl halides, or you can say the aromatic compounds, undergo nucleophilic substitution but under drastic conditions. Reason I have already explained when I started with the aryl halides. So therefore the reaction conditions are basically 623 Kelvin at 300 atmosphere. Nucleophilic substitution reactions of the aromatic compounds means to carry out the reactions under the simpler conditions, that is not to use those drastic conditions. For that matter, what we can do is that in the compound In the aromatic compound, what you do is you add any electron withdrawing group. Now that electron withdrawing group can be at the ortho position as well as at the para position, but at the para position its effect will be more pronounced. The reason behind it is that at the para position the electron withdrawing capacity is more than at the ortho position, because the para isomer has got the more number of resonating structures.